Welcome everybody, nice to see you here. Nice to be in Paris, it's a great honor. The topic of my talk today is locking the throne room and how ECMA Script 5 and the novelties in JavaScript and current JavaScript versions are probably going to be able to change the view on cross-site scripting on XSS. Just a word of warning, this talk is going to be very techy, so if you're not that much into JavaScript and into in-depth XSS, this might not be for you, but well, we'll see what we can make out of it. First, some words of introduction. My name is Mario. I'm currently employed by the Ruhr University in Bochum 2 days a week, researching for them an anti-malware solution, and I'm doing my PhD parallelly, and the rest of my time, which is 3 days a week, I'm working as a security researcher for Microsoft Redmond, and basically hardening IE9 or testing IE9, testing IE10. I'm also employed as a security consultant for several small companies or larger companies in Germany, several business networks and other websites. And I'm a published author and international speaker and created the HTML5 security cheat sheet. Some of you might know it, and back then I initiated the PHP IDS project. So that's about it. Today's menu, we're going to talk about JavaScript and cross-site scripting. Who of you here is into cross-site scripting or has played with cross-site scripting or at least knows what cross-site scripting is? Excellent. That's some people, that's great. So we're going to have some history lessons. We're going to see how it all began, how it started, what cross-site scripting is and why we have it. We will then majorly see what cross-site scripting is doing today, why it's a massive problem, why it increased in capability and an impact. We will have a look at current mitigation approaches, and we're going to see a little sneak peek into the petri dishes of current development of anti-cross-site scripting solutions. And then I'm going to try to introduce to you a rather new and different approach of defeating cross-site scripting and seeing what we can do during the next years to actually get hands on this problem. We're going to see a case study about this and talk a little bit about future work, and then we have hopefully some time left for a discussion and some questions. So let's just start. To fully understand cross-site scripting, we have to talk a little bit about JavaScript and what it is and what it does. So JavaScript was back then developed by Brendan Eich, back then called LiveScript, and JavaScript 1.0 was published in late 1995 by Netscape and first implemented in the Netscape browsers. Microsoft, of course, really liked JavaScript because it enabled the user to have some interactivity with the website, to have elements appear, disappear, and all that fancy stuff. And so they kind of recreated this and developed a dialect of the whole thing, which they call JScript. And it's still called JScript today, and if you're a developer and ever build websites, you know that there are major differences between JavaScript and JScript. It's like the same, but in the details there are major differences that can sometimes drive you nuts as a developer. After some years, this was in 1998, the ECMA 262 first edition was published, which was kind of standardizing JavaScript and defining several rules how JavaScript interpreters should handle the whole thing. And 2 years later, JavaScript 1.5 already came out, and synchronously JScript 5.5 was released. You notice the higher version number and sounds cooler and all these things. In 2006, so 6 years after that, apparently JavaScript 1.5 was very sufficient of fulfilling the needs of most developers. Back then, they released JavaScript 1.6, and 1.6 introduced a major novelty, which is still not implemented in any browser. It's just called E4X. Who of you has ever heard about E4X? So this is the most horrible thing you can ever imagine to happen in JavaScript, because it's saying we glue together XML and JavaScript. You have native XML support in JavaScript. You can just take any XML object, put it in the JavaScript engine, and it's going to parse, it's going to work, not yield any errors. I would love to show you some examples after the talk, because it would definitely burst the frame of this talk, but E4X is a horrible thing and it's definitely worth an own talk, and you're going to like it if you like XSS and haven't heard about it so far. Well, 2 years later, JavaScript 1.8 was released, bringing many novelties in terms of capabilities for the programmers. So you had the possibilities of using function expressions, you could use destructuring assignment, and a lot of stuff you usually just know from high-class languages such as C++ and comparable languages. And finally, in 2010, JavaScript 1.8.5 was released and was actually the first version of JavaScript being fully ECMA Script 5 compliant. What that means, we're going to see this later. So JavaScript and XSS are kind of glued together. It's in the name cross-site scripting. But let's think about what does XSS really mean, because nowadays we just see some website and someone's injecting some stuff saying like script alert XSS, script alert 1, whatever. Is that really cross-site scripting? I say no, we completely misuse this term. Cross-site scripting is coming back from the days when websites were usually using frames. We had like frame A and frame B, and they were able to script each other. And there was no such thing, such as the same origin policy or something like that. In the early days, it was just possible with Ajax or with just frames to just, for one domain, script the other domain and vice versa. And the actual first XSS attacks, classic XSS attacks, where one website was scripting a different website, a different domain, were reported in the late 90s. So if you have a look at Bugtrack and the old mailing list, you will see first XSS reports against early web applications. Today we know basically 3 major variations of cross-site scripting. The first one is the most common one, which is just reflected cross-site scripting. Okay, you have some URL parameter, some get parameter is vulnerable, or some post data or some post parameter is vulnerable and not filtered correctly, so you just put it in the URL or put it in a form, you submit the form or submit the URL, and then some markup is being injected and the stuff reflects. This is easy to detect, easy to conduct, and well, not the most complex of all vulnerabilities, and one might think this is easy to fix, but apparently it isn't. Then we have persistent XSS, which is just saying, okay, this stuff is stored. It's stored somewhere in the database, in the file system, it's just in the website, it's in the application. So it's hard to filter because it's part of the application. Someone injected it and then it's there. So there are no suspicious URL parameters or no suspicious post parameters or any other things that could indicate that there is an attack. This is, for example, the reason that NoScript and the IE8 XSS filter, as well as the Chrome XSS filter, is usually not capable of detecting persistent XSS, because it cannot distinguish between the actual injection and the legitimate code of the website. And then we have one of my favorite kinds of XSS, which is DOM-based XSS or DOM XSS, which brings a special problem. Who here knows what the big difference between the first kinds of XSS and DOM XSS is? Yep. Exactly, and that is the most important thing here. DOM XSS is not seen by the server. So if you have a server-side solution for filtering your markup, filtering your input, DOM XSS is completely bypassing it because it does not reach the servers, exclusively using client-side properties to conduct the damage it wants. So we're going to see some examples later on, and first going to move on with XSS and the basics about it. XSS is usually used to conduct information theft, information modification, user impersonation, and sometimes to leverage more complex attacks. If you guys, for example, remember the attacks against Apache, I think it was starting with an XSS in Jira, like in their code versioning system, and then was kind of elevated to actual code access and code execution and compromisal of the files on the web server. But it all started with an XSS, and there are many examples of real-life attacks that initially started with XSS. Oh, that was the wrong one. So let's talk about the DOM a little bit to just introduce the whole thing. The document object model. The document object model is a prototype-based representation of HTML or XML trees. So every single HTML element you have on a website in the markup, in the HTML, will have a representing object node in the DOM. So you can play with it, you can remove it, you can modify it, you can extend it, you can put stuff in there. The DOM provides many interfaces for easy JavaScript access. So the DOM is not JavaScript, it's just the glue between the markup and the JavaScript engine. And furthermore provides several methods to read and manipulate DOM subtrees and just, like I said, remove stuff, add stuff, fill stuff, change attributes, change behavior, and so on. The DOM also provides an interface for dealing with events. So you can, for example, say, hey, I'm a website and I have this area, this is red, and if you hover me, I'm turning green or something else. And this is an event playing an important role here because there's a mouse over, you're hovering the event, so the mouse over event is being fired and something's going to happen in the JavaScript to do some changes. The DOM also allows interaction with browser properties. One of these browser properties, for example, is the object navigator, where you will find the user agent string, what browser you're currently using, the screen resolution, there's a screen object and all these things. And some of these objects are kind of magic and do not behave as other objects do. And one of these horrible, magically behaving objects is actually location. So in the DOM, you can go along and say, okay, location.href equals something, and then a redirect happens. Or just location equals something, and then again a redirect happens. So you can just do a simple string assignment on the location property, and it's completely whack up the whole thing. It's just completely changing anything because you're going to be led to a different site. If you then go ahead and say, for example, like location equals JavaScript alert 1, you have an XSS because you execute JavaScript just by assigning a string to location. And this is kind of taking care of the fact that one of my favorite XSS vectors is possible this way, which is not containing any parentheses, but still executing arbitrary code. And this is just saying location equals name. And location equals name just says, okay, I assign the property of the variable name to location. Name can be set from a different domain in the same tab, because it's back then from the old ages when we were using frames. And you have a vector which doesn't use any parentheses and is likely to bypass most filter systems. It did bypass many XSS filters installed in browsers such as IE and Chrome back then, but it's fixed meanwhile. But back to the DOM, it also provides several proprietary interfaces depending on which browser you use. Firefox, for example, is providing a crypto object which you can use. There's a hidden eval in there. You will find it if you look closely. There is access to several browser components. If you have a close look at the Firefox/Mozilla DOM, you will find a lot of properties that you will not find anywhere else, which are leading you deep into the guts of Firefox and allowing you to change some stuff or to interact with some interesting APIs. Of course, IE is shipping a lot of proprietary DOM properties, Chrome as well, actually. And of course, you have the possibility to use the DOM to interact with CSS, with style sheets, and to just change the appearance of elements without changing the element itself. Cross-site scripting today, I would go as far and say that cross-site scripting is a quite ancient problem. We know this problem for 10 years, and still we did not manage to fix it. It's still around, and it's getting worse every day. So what are we doing wrong here? Why is this problem still unsolved? Well, there are some reasons for this, actually, and we're soon going to the live demos, which I hope you're going to like. But let's iterate through the problems. The first of all is, of course, complexity. Like web applications, modern web applications are really complex things. If you have a look at the source code of, for example, Gmail, like the stuff you can see in the client, it's massive. Like there is so many methods, there are so many APIs, there are so many interfaces. It's extremely hard to grasp this huge application for one person in, let's just say, a month or 2 months. It's just almost impossible. There are so many man-years of development just in the client-side component of Gmail or comparable tools that you can say it's intensely complex. So if there is an XSS hiding somewhere in this code, this is not a big surprise. Then, of course, we have the biggest problem, or one of the biggest problems, which is browser bugs. So even if the website is sane, even if the website is well protected against cross-site scripting attacks, as an attacker, you can still ignore it and still conduct cross-site scripting attacks by just abusing browser bugs. We have, of course, insecure web applications, which is the cheapest of all reasons. We have browser plugins, which are able of executing JavaScript. So, for example, Java applets can execute JavaScript, of course. There's an object doing that called JS Object, invented by Netscape. We have Flash, which, of course, can execute JavaScript. We have PDFs, which, of course, can execute JavaScript. We have QuickTime movies, which, of course, can execute JavaScript. And the list goes on. Whatever you take, every single plugin is somehow capable of executing JavaScript and thus conducting cross-site scripting. And now here's my favorite thing. I put it a little bit in emphasis, which is impedance mismatches. Who of you could imagine what impedance mismatches could be in the context of cross-site scripting? No one? That's great. So we have a live demo what impedance mismatches are. So here we have, let's start simple. Here we have Firefox. Oh no, this is not Firefox, this is IE. Just a second. Here we have Firefox. I think it's the latest 3.6 branch. And I created a little tool which is not doing anything complex. It's just a text area, and when I type something in this text area, it will be taken and reflected, and I can see what the browser is doing with my input. So if I enter some markup, I can see what the browser is internally doing with the markup by just reading the inner HTML property. Let's give it a small example. We just create a very, very simple tag, which is the strike tag. Just close it, because I'm a nice guy. And you can see it reflects here. And this is the actual result the browser is doing internally. Do you see a difference? No, because there is no difference. Firefox is a nice guy. There is no difference. You will see the differences soon. Let's have a look, for example, what IE is doing. Again, create an as tag and close the whole thing. And we can see, okay, there is a small difference here. Can you spot the difference? Well, basically, IE is taking the markup and putting the text to be uppercase and not lowercase. I'm using lowercase here, but the browser automatically casts them to uppercase. And you might think like, okay, well, who cares? I don't see any problems here. That could not possibly be exploitable. And it's not. But let's move on. Let's, for example, go ahead and say we give this little fellow a class. And we are such a nice developer, we just say class, and we even quote it correctly. Like we use everything right here. We have lowercase tags, we have the class attribute equals and double quotes. But where is my class? It's just not here. It didn't arrive yet. So IE realizes that my class attribute is empty, and thus just strips it. Well, who needs empty class? It's completely useless, just eats performance, so throw it away. As soon as we put something in here, let's just say a 0, it suddenly appears. Still uppercase, here's the 0, and wait a second, where are my quotes? Well, quotes are expensive. Quotes need to be parsed, so we just omit them for performance reasons. Who needs quotes? And you might think, okay, that is nasty. If I now go along and inject a white space, then I have an injection, do I? No, because Internet Explorer is pretty smart and realizes that. Says, okay, there is a white space that could be a possible attack, and let's just add the quotes, it's better. So I remove it, and I think, okay, if I cannot use white space, I can maybe use the single quote. Let's have a look at the single quote. And again, Internet Explorer realizes this and automatically adds the quotes. So we might think, okay, what can we do here? And what I'm going to show you now is meanwhile fixed, but it's an extremely nasty injection, and it's working against almost every single website out there. So this is kind of XSS, but it's fixed. So, and it's published, so I can talk about that. What other possibility is there in Internet Explorer to actually delimit attributes? We have none at all, we have double quotes, we have single quotes, and we have, who knows it? Huh? Nah, not exactly. Nullbyte is of course working everywhere, it's just going to be stripped from anything in the DOM. But we have a different delimiter for attributes. This is my favorite delimiter, and it's actually one of my, Again? Nope, it's the backtick. Let's have a look at this fella. This is working as well. It's a valid delimiter. You see, it doesn't appear down here, but it limits the attribute. So if we go along and add these backticks, or go back and use these two fellas, and then add the backticks, you will notice that something is horribly wrong here. The double quotes do not appear, just the backticks. So we just ended the class attribute in the processed markup. So we say onClick equals alert1. And we just add some content because I forgot that. And we see this is kind of very suspicious, and we click it. This is the rendered markup, and it alerts. So we have an injection. We have an injection with completely... Thank you. We have an injection with completely valid markup. There is nothing wrong with this markup. Your server-side filter, such as HTML purifier, cases, or whatever, will say, this is completely okay. There is no problem with it. No violation has taken place. But the client will say, the browser will say, oh, I don't know how to parse this, so let's just make it an injection. But it's worse. It's actually worse. You can, of course, automatize this and use just an image tag to inject here, so you don't have any user interaction, which is necessary. But I'm going to show you another example. In HTML, there are several tags, and I think it's a family of about 90 tags with tons of attributes in all HTML versions combined. But of course, there are still some letters in the alphabet which are not being used for tags, which are unknown tags or unknown elements in the end. So let's just go ahead and create an unknown element. Nobody knows the X tag. The X tag does not exist. So we just write this tag. Where is it? It's not appearing. We don't know. Let's give it some content. Oh, here it is, but it's just the content. The tag is missing. Well, that's weird. Let's be nice and close it. Now we have only the closing tag, not the opening tag. What the? This cannot be. So we add some content here. Oh, there it is. It appears. So here we are. Now we have the complete tag. Like, of course, this is completely expected behavior, isn't? No, it isn't. So, since we have a completely unknown tag, we might want to specify what kind of tag this is, what kind of behavior is applied to this tag. And one way to do this is giving it a namespace, assigning a namespace. So we just go ahead and say xmlns equals. And we see, okay, here we can use an empty namespace and it's still being rendered, unlike the class thing. So, but still nothing really special here. It's not far away, so the output is not far away from the actual input. So now I will ask you, what will happen if I actually give it a namespace? Whatever kind of namespace it is, if I actually give it one. Who knows what will happen? Because this is an awesome example. Should I just give it a namespace? Let's try it out. The whole thing completely explodes. Suddenly we have a processing instruction which is huge. We're saying XML, namespace, space, prefix, equals, some weird delimiters like rectangular brackets, then a zero just standing in the middle of the room, then namespace again, then a quoted namespace, then the whole thing closes, and then we have the tag. You might say, what the heck is this? How is this even possible? Well, this is possible with unknown tags. I can show this because most HTML filters do not allow unknown tags, so this is not a XSS. If you have an HTML filter which does allow unknown tags, you're screwed. But it's even worse. So you can see we have the zero here, and the zero is being reflected here and here. This one is unquoted, so that means if we just close the whole thing, we're creating doom and havoc over here. You can see it already. We just start a new tag inside the namespace. You can see it struck, and we just successfully injected the tag. So we're going to be nasty. We say image source equals x on error equals alert 1. What a namespace, I say. Just forgot the equals and blink. There are these. But it's worse. It's even worse than that. Let me show you a different example. So we have a namespace, and there is the possibility of passing in the namespace with an arbitrary string or with an actual URI or a fully quite domain name identifier, or we can use this URN scheme, which is common for many Microsoft products. And we can just say, for example, URN : and just say foobar. And you can see there is not much difference. It's the same thing. Here we have the unquoted representation, here we have the quoted representation, and this is staying the same. So this is not special. But let's assume we're not that nice of a developer and we're a little bit nasty and we destroy the closing tags. What is going to happen now? Something, again, completely different. Now we suddenly have the namespace positioned here. We have the actual tag name, and then we have the namespace. So let's see what we can make out of it. img space, oh, it works, source equals x, oopsie, sorry, on error equals alert 1. Oops. There we go. This is yet another way of completely confusing the parser. So again, the server will say, well, there is nothing wrong with this tag. It's just an unknown tag with a valid namespace, kind of valid namespace. Okay, it contains spaces and stuff. But the result rendered by the client is completely different from anything we put in there. It's like there is no relation anymore. And we can easily fool any server-side filtering component by just giving it this kind of markup. And it's not just IE. You will find these kind of impedance mismatches in any browser. There's a very funny example in Firefox which I like to show. With the simplest of all HTML elements. What is the simplest and the most easiest to grasp HTML element? It's of course the comment. Like the comment is just commenting stuff out. So it's easy to build. You just go ahead and say, okay, we started with the lesser than, exclamation mark, double minus, and double minus again, and we have a comment. You can see nothing is here. We say, for example, A and B, and it has no visual impact. And you can see the representation of the browser is here. This is Firefox 3.6, I think 13 or something like that. But what happens if we play with the comment, if we vary it a little bit? This is still a valid comment. This is not a valid comment. Suddenly we have entities. Still everything okay. Still not a valid comment. Still entities. Oh, that's a valid comment. Like, where did these fellows come from? Suddenly we have like 1, 2, 3, 4, 5, 6. No, just 5. Of dashes just appearing out of nothing. And if you just build it up again, say, okay, 2 dashes. Nah, no comment. 3 dashes. Ah, no comment. 4 dashes. Oh, we have a valid comment. 5 dashes. Everything okay, just remove 1. 6 dashes. Ooh, it's not a comment anymore. 7 dashes. Ooh, it's not a comment anymore. 8 dashes. Oh, it's a comment again. 9 dashes, and so on. So what is the browser doing here? This is nuts. Like, this is completely nuts. And since we have a little bit more time, I just want to show you a different example. Because this is working, for example, for CSS as well, for style attributes. So let's take a list item. We have a list item, just a standard li tag. Oops. And we fill it with some stuff and say 1, 2, 3. And then we say, okay, style equals. And we say, for example, font family, one of my favorite properties. And we are nice guys. We just coded correctly. And we say, okay, what can we do here? We have font family, and we can put something in here, and it's going to be reflected. What ways do we have to represent characters in CSS inside the string? It's, of course, CSS escapes. So the hexadecimal ASCII table value plus a slash, which is trailing the whole thing. Let's try this. You see, /j, doesn't do anything. What if we take, for example, the 27, which is the representation for the single quote? This is a safe way of masking strings, but still, the output is giving me an actual single quote. This is horrible. This should never happen. So what I'm doing right now is just doing 3b, which is the semicolon, which is ending the CSS property. Then I say x, and then I'm saying 3a, which is doing a colon, and then I'm saying, for example, expression alert 1. It's not executing right now because we are in IE8 mode and not in IE7 mode. But you can see we have a complete injection here, font family, colon, correct quotings, then the font family string ends. We start a new property, which is called x. We assign expression, we say alert 1, we end the whole thing, and down we are. We have a successful cross-site scripting attack deployed inside a valid font family string. And this is just yet one more way of kind of demonstrating impedance mismatches. There are so many vectors. Like if you take inline SVG, SVG files themselves, several other attributes, unknown tags, and all these things, there's a huge bunch of possibilities to kind of play with these things and completely vary the output from the input and thus create injections. And if you're a website pen tester, like this backtick tricks work everywhere. They work on almost every single website because it's extremely hard to fix. Like what could you do? You could, for example, go ahead and encode them to HTML entities, but you're inside an attribute, so encoding won't do you any good. It's the same bug. It's still there. So you have to strip them or replace them or kind of think about some way to actually fix this problem. And it's really complicated. Like every time we really have to discuss with customers and say like, okay, the best way to fix this the backtick issue is like doing this and replacing it by a Unicode representation or something like that. But it's always kind of quirky and not always working on the first attempt to fix the bug. So what else can we do about, what else can we see about XSS? We see a lot of application layer mitigation concept. This is basically saying we have something running on the server, some server-side filter who's trying to just fix the stuff to kind of sanitize, filter the markup and doing things. This is a problem. You just saw why, because one can easily trick those server-side filters. We then have, of course, one more reason why XSS is still a problem, which is risk assessment and ignorance. So in many cases, we had the situation, this is just an alert. No, it's not just an alert. Yeah, we can just, it's not so bad. Let's just fix it later on. It's not so important. So users or developers do not correctly estimate the danger of XSS. And of course, we have one of the biggest problems out there right now, which is called HTML5 or HTML the living standard, which is constantly adding tons of new features and saying, okay, this is new, we have to do this, we have to do this. I can show you examples after the talk of proposed HTML5 features which just extremely blow. Like, this is completely impossible what you can see there, but this is the topic of a different talk. We're going to see this later. So, we end up with realizing that XSS is not a server problem, it's not a network problem, it's a user agent problem. It's explicitly a user agent problem, nothing else. I'm not saying this is a browser problem. Why I'm not saying it's a browser problem, but a user agent problem? Because there are other tools acting like browsers. Your Skype, your Instant Messenger, your installer of applications, they all render HTML in some way, so they all act like browsers. They render HTML, but they are user agents, so it's just a more generalized term. But in the end, XSS cross-site scripting remains a user agent problem and nothing else. So let's talk a little bit about the mitigation history. How did we try to fix XSS and how did we fail that epically over the last 10 years? If we have a look at the server side, we can see a lot of native runtime functions. Let's, for example, take PHP. In PHP, we have this awesome function called scripttext. And scripttext is just stripping HTML and done we are. Like everything which is inside lesser than and greater than is just going to leave the string and the rest is going to be displayed or used later on. Scripttext is very restrictive and not really cool for rich internet applications who want to allow the user to post or to use certain tags, for example, the harmless A tag or the harmless B tag or stuff like that. So back then, the PHP developers came up with an awesome idea and saying scripttext should be just getting a second parameter, which is a string, a comma-separated list of tags which I allow for being getting through to the script text filtering. You might think like a comma-separated list of tags in a string. This is nuts. So how can we, for example, control attributes with it if I want links, but I don't want on-click in that link? Can I do this with script text? Short answer, no, you can't. Script text sucks. Then we have HTML entities, which is just converting every suspicious character to the entity representation. You just saw with a backtick trick how you can fool HTML entities and get past that in many situations. So HTML entities doesn't work either, and it's not even remotely capable of handling the needs of developers for rich internet applications, because it just encodes everything, and it even does it wrong. There were so many occasions where HTML entities was bypassed by using UTF-7 or other exotic char sets, and you can just not use it. There is even a current bug in HTML entities. When you take broken UTF-8 characters and pass them in, then you can find a way to just bypass it and still generate lesser than and greater than characters or even double quotes to conduct your XSS attack. Well, then we have runtime libraries, which are running on the server, such as mod security, just detecting stuff, trying to prevent stuff, trying to validate the request, to have a look at the packages and find out if there's something malicious in there. Basically working with regular expressions. So this thing gets a string, it has a look at the whole thing, says, hey, is there some matches? If there is a match, it's evil, and throw it out, and done you are. So you can imagine how crappy that is in the end. But still, people are using it. Mod security is still around. Then we have, for example, a lot of external libraries filtering input and output. One of the most powerful, I would say, is the HTML purifier. PHP people among you might know it. We have Anti-Semi, which is a great software, which is actually an OWASP project. Hard to bypass, but possible to bypass. We have KSS, which is the crappiest filter I've ever seen. Do not use it ever. We have Anti-XSS and Safe HTML from Microsoft. We're working on hardening it. It's not always easy. We have interesting mitigation concepts such as HTTP-only cookies, which is saying, okay, only HTTP requests can access my cookies, JavaScript can't. I think it's pathetic, like an advanced attacker would never access the cookies. Like, what do you want with the cookies? Screw the cookies. So much more attractive targets in an attack website, but cookies. Who needs cookies? And we have, of course, the client-side protection mechanisms. One of these is two-static HTML, a Microsoft invention which was first implemented in IE8. And allows JavaScript to filter markup and to receive untrusted strings and turn them into trusted markup strings. And of course we have NoScript, which is a great extension but has its design flaws. I'm using it, but I'm not liking it. And but still there is nothing better out there as far as I would see. We have also the WebKit XSS auditor, which is meanwhile being deployed in Chrome as well. So if you have a reflected XSS attack, Chrome is likely to notice it and block it, which is quite interesting, but again, bypassed. And we have upcoming approaches such as CSP, the Content Security Policy, which is just allowing a developer to specify via headers what kind of resources, what kind of interactive resources a website is allowed to use. Shall there be an eval? Shall there be function constructors? Shall there be external scripts? If there shall be external script, from where should they come? Should they be allowed to come from only Google Analytics? Should they be coming from any domain or just certain domains? This is quite interesting and definitely worth a look. But again, already broken in several ways. Not going to elaborate on this one. We can discuss this later over some beer, but it's broken. So, we already saw some examples for the impedance mismatch. And basically, the whole problem here is that web application security is layer-based security. You have many layers which are playing together or playing against each other and cannot really be aware of what the other layer is doing. They're just passing stuff through. And as you notice with the live demo, often layer A is unaware of layer B's capabilities. Like, how can layer A know what layer B is capable of? How can the server know what the client is capable of? They can, of course, exchange the user agent string and some kind of think, okay, this browser can do this browser can do that, but that can all be forged, like user agent strings are forgeable. So there is no actual way of passing trustable information about capabilities of a client. And there is a nice case study on that, which was targeted against HTML Purifier 4.1.1. It's, I think, meanwhile, almost half a year ago, maybe even a bit longer, and I was breaking it with a rather interesting trick. And you can see the vector right here. So I injected an A tag, just a harmless link, giving a style attribute, giving the background property, giving the URL handler. And now here's the interesting part. Who can spot the most interesting character, taking care of that this is A, an injection, B, executing JavaScript, and C, even bypassing HTML Purifier? Who can spot the character? Well, it's a little bit difficult, and I have to confess I found it by fuzzing, so that was the most good way to find it. It's just I enumerated some characters and suddenly an alert popped up and I was like, what the hell, this is not possible. The interesting character here is the exclamation mark. Inside a correctly quoted string, back then for IE8, the exclamation mark followed by another special character, in this situation the @ but you can choose whatever you want, you can choose another exclamation mark or whatever, was doing one thing, and it was breaking the string, declaring a new property, even adding automatically the semicolon to end the property and initiate a new one. So this actually executed. Here, the background URL ends. We don't need the parentheses. We don't need the single quote. We don't need the semicolon. This is all being done by the exclamation mark and another special character. Try it out with old IE8s. It's still going to work. HTML Purifier took 3 attempts to successfully fix it. The first attempt was broken with CSS escapes, and the second attempt was broken with some / magic, just confusing the parser of HTML Purifier. So you can see there was a way to fix this on the server as well, but it was extremely complicated. So Edward was taking 3 attempts to actually successfully fix it. And this is again pointing to the problem. How can layer A, which is implying a protection software or protection mechanism, know what layer B is capable of? Even Microsoft didn't know that this is possible. And they were like, who wrote this code? This is incredible. We have no idea why this works. But you can see this was completely rendering all server-side filters useless. With one character, with an exclamation mark. Even the character is nice for that. And there are so many more examples. We have seen some of the real-world attack samples already. And they are just giving us the possibility to make website vulnerable against XSS, which basically are not, like which are completely well protected against the XSS we know, like the known bad. We have the possibility of the exploding XML namespaces. We can generate text from just thin air, like you saw with the other namespace trick. We can exploit CSS escapes. We have the backtick tricks, and so on. There's so many more things. And there's even more vectors the server can never see, which I already mentioned, which is plugin-based XSS. We have the Adobe Reader, which is capable of executing stuff, Java applets, Flash Player, QuickTime videos, SVG images. And we even have more critical stuff like charset injections, content sniffing. We can do nasty stuff, still do nasty stuff with UTF-7, which is the weirdest charset ever, in my opinion. We have EBCDIC or AppStick. Who still knows AppStick? Like, the older people should know AppStick. Like, it's one of the old IBM mainframe charsets and still supported by browsers. Like, they still do this. And the bad thing with this charset is actually that the position in the table, in the character table, for lesser than and greater than, are not the same as in the ASCII table. In the ASCII table, the lesser than is 3C and the greater than is 3E. In AppStick, it's 4B and 4D. So whenever you inject AppStick stuff and you can force the browser to actually render this at AppStick, you can do anything. You can inject any character and it's definitely going to bypass the filter because the filter is just a 4B and a 4D. So let's just give it through. We have some examples with McFarcy. I don't know who of you is following Ashigawa Yuzuka on Twitter. He was tweeting a vector which was abusing a bug in the McFarcy implementation of Firefox, which was initiating the tag with a moon, then saying script, and then a sun to close it, and then alert 1, and then again a moon / script and a sun. It was a beautiful vector. Let me check if I have internet connection here right now, because if I do, I'm just going to have to show it to you. I have the feeling we're running a little bit out of time, so I have to rush a bit. Nah, that doesn't work. We're going to see this later. So, and we have DOM.XSS, another vector which is never striking the server. The server cannot see this. So, server-side protection, well, we cannot really use it. It's not effective. It will never fix XSS. Whatever we do, the server cannot help fixing XSS. Like I said, we have plugins, we have DOM.XSS, we have so many eccentric ways of executing JavaScript. We have seemingly harmless text executing unrolling JavaScript execution and so on. So I'm stating here right now the server cannot serve protection for the client at all. It's just not possible. I don't see any way of the server doing that. So what can we do? Let's revisit XSS itself. XSS attacks target the client. XSS attacks are being executed client-side. XSS attacks aim for client-side data and control. XSS attacks impersonate the user, again happening on the client. So XSS is a client-side problem and nothing else. It's nothing to do with network security, server security, operating system security. It's exclusively a client-side problem. Sometimes it's caused by server-side vulns and stuff like that, but it happens on the client. But still we try to improve server-side filters, which is completely useless in my opinion. So my idea was to define a different approach of actually tackling XSS. And my idea was to implement some prevention against XSS attacks in the DOM itself, in the document object model. And I'm trying to go for a capability-based DOM security model. And the inspiration was HTTP only because it's basically doing the same, limiting stuff down, forbidding access to cookies. And I know HTTP only is a little bit pathetic, but the next examples I'm going to show you are trying to demonstrate how we can implement HTTP only in the client with just some few lines of JavaScript. So, the first prototype we wrote for the way of creating a DOM which is trustable, which is self-aware of attacks, was using a proprietary property which is called, or proprietary method which is called Affine Getter. So here we have an example where we want to block cookie access. So we go along, we take document, which is the document object, we call the method Affine Getter. We define the getter for the property cookie. We assign a function for this getter access. We say alert no cookie access and we return false. If the attacker now goes along and says alert document cookie, there will be something else. There will be an alert saying no cookie access, my friend, you cannot have this. Well, fair enough. But this approach is crude, like it's really, really, really bad. Who can spot why it's bad? Like this is complete nonsense what I just showed here, and just to show how the general approach is working. First problem, only working in Firefox and Chrome. So it's not working in IE, it's not really working in Opera, and it has a little bit of trouble in Safari. It's loud, an attacker can easily fingerprint that stuff, and it's not tamper resistant at all, because JavaScript is providing one fierce operator which is called the delete operator. If you delete something, you will take a property and put it back, reset it to its original native state. So how would the attacker bypass my approach here? Again, the same code. I'm just defining the getter for document cookie, so we cannot reach it with a standard alert. And the attacker goes along, says delete document cookie, alert document cookie, and there we go. The attacker has the cookie. So this approach is obviously bull, so we can't use it. So over the time, we tried to find a way to find some actual tamper resistance for objects. How could we really freeze or seal an object and make sure that the attacker, even if aware about the protective code around the object, cannot destroy it, cannot get hands on this object? And to be honest, we played with a lot of things. We played with document __ proto and Affine Getter. We played with the constructor, going down to the prototype of the constructor. We played with the Firefox guts, which is findable in the components constructor. We're playing with lookup method, trying to define it there, overwrite it, redefine it, and all that stuff. And we never found a way to make it really tamper safe. And it really sucked. The whole project was kind of on the verge of existence because we couldn't do what we wanted to do. At some point, we just figured out that JavaScript 1.8 and 1.8.1 is completely unsuitable for DOM-based protection. So we learned that, and luckily there was ECMAScript 5. And the first implementation in JavaScript, fully supporting ECMAScript 5, was JavaScript 1.5, available in Firefox, 4, available in Chrome, most versions, available in IE9, available in Opera 11, and available in Safari 5, which is quite nice. So we have a new JavaScript engine, which is giving us more features, and which maybe might help to tackle this problem a little bit better. So the basic novelty we have with ECMAScript 5, the most important novelty in my eyes, and the most important novelty regarding client-side XSS mitigation or even eradication are the object extensions. So now we have object freeze, object seal, most importantly object define property, and object prevent extension, and some other methods which are there but not that relevant for us right now. We also have proxy objects, which is a very interesting thing. We cannot use DOM proxies right now because it's just for userland objects, but we're trying to urge browser vendors to implement this as well. We have more metaprogramming APIs, and we have fine DOM level 3 events registering any change in any markup trees, subtrees, and so on. But most importantly, we have defined property. So what is this doing? What is object defined property doing? Basically, object defined property is capable of defining a property. What a surprise. We have 3 parameters. We have the parent object we want to define upon. We have the child object, which we actually want to really defined, like we have the parent object and the child object, like with define setter, and we have a descriptor literal. And with this descriptor literal, we can pass in some properties on how to define this and how to kind of take care about the state of this object. The first is get and set. We can just define a setter, we can define a getter. The second one is value. We can just set the value of the object. Could be a function, could be a string, could be an integer, whatever we take, or a number. Then we have the enumerability. Can it be seen when the object is being looped in a for-in loop? We have the writability. No need to comment on that. It's just, can you write it or not? And most importantly, we have the configurability. Let's have a look on how this looks like. Again, same thing. We want to protect document cookie, because it's our core asset here in this example application. Now we don't do this define getter stuff. We just say object, define property, document, the parent object, cookie, the child object, represented as a string, and then the descriptor literal. We're saying the getter will only return false. The setter, if we try to overwrite document cookie, will only return false. And the whole thing is not configurable. We say configurable false, because this is putting the whole thing in a tamper safe state. If the attacker now goes along and uses his magic trick against our protection mechanism and says delete document cookie, then alert document cookie, he will get false. There will be no cookie access. He cannot access this property anymore. It's gone. It's completely gone from access. Configurable false is final. Whatever you do, you cannot override configurability anymore after you set it. Of course, you can just reload the page. But on this very same page, you cannot override it anymore. It's a final state. So whatever you do, whatever the attacker is trying, he cannot get access to this property anymore, which is awesome, which is extremely dangerous, but as well awesome. We tried several things to attack it. We tried prototype deletion. We overrode the constructor. We even used the components lookup method tricks and so on. And we found no way to actually get hands on the real property if it is protected with configurable false. The problem here is it's a little bit of a philosophical dilemma which we have here, because we can do this as defenders, but the attacker can do this as well, can also freeze stuff and modify stuff so no one else can change it, even if they do delete or try to reset stuff. Also, we kind of working with a prohibition-based process here. We are regulating access in general. We say no one can do this, no one can touch cookie anymore. But sometimes it's a little bit too strict. Sometimes we want some methods to be able to access document cookie and some not, especially not the unknown, the ones we have not registered in our application, in our DOM. We're going to see how we approach this problem later on, but what we can also do is, for example, use this to protect HTML elements. Let's have a look at that. Here we have one classic thing. We have a form, and this form is, for example, leading to a login or something like that. And we want to make sure that an XSS cannot change the form action anymore, cannot redirect the form to another domain to steal the login data, which is happening all the time. This is one of the most common XSS post-exploitation techniques. So we take the form, we just find it in the DOM, we just request it here, then we again call object define property form, then we take the property action, and we apply our fantasy method IDS detect hijacking to the setter and IDS detect stealing to the getter, and we all seal it with configurable false. If then the attacker goes along and says, hey, document forms 0 action equals evil.com to steal the login data, this wouldn't succeed because the form action is blocked. So, interesting. And it's time for a first roundup. We have the possibility of delivering actual access prohibition. It might be effective in very simple cases, like protecting document cookie, to protecting form actions, and so on. And we have the possibility to make it tamper safe. And we actually now have the foundation for a client-side IDS. This is what we can deliver right now, because this is the most important thing for a client-side IDS, is tamper safety, that you cannot touch it from the outside, you cannot modify its states. Another good thing here is that we don't know impedance mismatches anymore. All this stuff does not exist anymore because the data we are getting, we are processing on, is happening right in the DOM. We are there where all these filters already have been circumvented, already have been bypassed, and whatever is coming, whatever is landing in the DOM is the actual unobfuscated code because it's already there. So charset's trickery, impedance mismatches, we don't care about in this approach. We completely clearly see everything that is happening in plain text because the DOM is kind of executing the whole stuff and giving us the exact automatic quasi-normalization we need here. The limitations are clear. It's a blacklisting-based approach. We can just say this property and everything else we don't. It's a little bit complicated to keep up the continuity, to just be sure that after 10 minutes of using the same page, if it's a rich page you do not refresh all the time, such as Gmail, that it still works, that if new elements are being created, that they're also protected as well. And it might, of course, have the problem of breaking existing own JavaScript applications. So it's hard, for example, to build such an approach to be fully working with jQuery or Google Analytics or other things. And in many situations, just forbidding access is way too restrictive. So what we're seeing right now with the current approach is a possible small adoption rate, high testing effort. Many web applications would be breaking, and it's not really intelligent or smart or even fine-grained. So let's go a little bit further, and we're almost running out of time, some 10 minutes left. What would happen if we just do not forbid access to the properties, but kind of install a system in the DOM, which is of course sealed as well, and provide a little role-based access control system inside the DOM, inside the now tamper-safe DOM? For example, if you have a look at the protocol dance I'm showing here, let object A know which methods can access it, can set it, can change it. When some other method is coming and trying to actually access object A or any other property, the object is going to look up the function, hey, are you in the list of trusted accessors or setters, or are you not? If that's the case, I will allow you to pass. If not, thou shalt not pass. And I just think I skipped the slide. So let's have a look at a small example. Here we have the same thing, and now we're using our fantasy IDS and again a fantasy role-based access control system. We again go along saying object-defined property. We again choose document. We again redefine cookie. Whoops. I have some problem with the scrolling here. I'm sorry. Okay, we're back. And we see that in case there is a setter access on document cookie, we call the role-based access control system to check the setter if it's allowed, if it's authorized to actually perform this operation. Then we put the whole stuff inside the, or we call the IDS function, which is checking the arguments. If something suspicious is there, an overlong string, some stuff indicating XSS. And we do the same, of course, for the getter, and we then seal it with configurable false. And if we then, for example, have a legitimate call to extract the value of document cookie coming from, let's just say, the my object, calling with allowed method, which is, of course, allowed then we can access document cookie without any problems. But if the attacker goes along and says alert document cookie, it wouldn't work anymore, because alert is not in the list of defined functions. And you might ask, okay, why does the attacker then not just override my allowed method? Well, because it's sealed. He cannot. Like, we just seal the variable my, and done we are. So there is no spoofing. And there's also a kind of forced introspection we're applying here. We can take existing properties and we can just give them more capabilities of controlling themselves, of knowing who is attempting to set or to get them or to even execute them. We can tell a function who is allowed, which other function is allowed to call that function. So we just, for example, check against our arguments callie caller, then we know who tries to call that function. If we seal that off, if we put that in a whitelist, there is some functions allowed to call this function or method and some others which aren't. And we can easily control the whole DOM with that. And again, we have tamper resistance thanks to configurable faults. So this might all sound a little bit like a fantasy project, not really working for real-life applications. So I want to present you a case study we did. And this case study is using the Stanford JavaScript crypto library, which is an actual library used by many applications out there. I think even the Helios voting application, which is generating a little bit of buzz right now, is aiming to use the JCL, I hate this acronym, and trying to provide pure JavaScript crypto. It provides a lot of method and is capable of using AES, SHA hashes, HMAC, and so on. It's all in JavaScript. It's all completely implemented in JavaScript. And when you have a look at the website, where SJCL is being advertised by its developers, they say it's secure. So it's even formally proved that it's secure. All this crypto is fine. It's safe. You can use it. But some paragraphs later it says, it's not that secure if you have an XSS. So just screw it. And an XSS in an application using client-side crypto is obviously something critical. Like if you have an XSS in such an application, something is screwed up very badly, because if you don't have anything sensitive here, you don't need the crypto. So it's like a catch-22. So what can we do to use our new technique to actually protect the Stanford JavaScript crypto library? Well, it's easy. We just seal it. It uses global variables. Global variables usage in JavaScript is not very hip. Usually developers tend to not use global variables because they say, they're in the global scope and everybody can change them, everybody can watch what's inside. We should rather use anonymous function enclosures. So get away from global variables. I'm stating right now that global variable usage in JavaScript is cool because you can seal them very easily. You just take the whole thing, seal it, and no one can access it anymore or just modify it anymore. So we sealed the SJCL and it still worked fine, and we couldn't modify it anymore, at least not on modern browsers. But there was more to do. The library was also using not only using global variables, but using native functions and native objects. Some of them was math floor, math max, math random, document attach event, and things like that. But in the end, it turned out to be just a handful of methods and just a handful of properties it was using from the native DOM. So we wrapped them too, we sealed them too, made sure nobody can touch them and nobody can overwrite them. And actually, after that, we tried to attack the SJCL and had other people try to attack it, and we couldn't break it anymore. Because initially, the design was horrible because it's using global variables, but you just went along and we sealed that global variable, sealed all the DOM methods being used by this global variable, and done we were. It's like no one could modify it anymore. Then the user could actually trust the crypto methods. Case study number 2, browser exploitation framework. Many of you might know it, Beef. Not as seen some minutes ago. Yeah, that was still from the conference, I'm sorry. But Beef is a nice project. It's just basically giving you the possibility of taking in a website where you already had an injection, put some JavaScript in, develop a back channel, and then remote control this website. I don't use it myself. It's basically post-exploitation, but still quite a nice of a framework. But the problem is, you can counterattack Beef. You can beef the Beef, because Beef is using a global variable in its hook. And if you have a website which is aware of having some XSS bugs and they are hard to fix, but also knows that there might be an attacker beefing that website, you just build some simple mechanism to detect the moment where there is the global beef variable, modify everything in this variable, send stuff back to Beef, and F it up. And this is possible, and this was possible, and if there is one XSS in Beef itself in the control interface, you can completely remote control everything which is happening in Beef with a website which is just sending back data. So I was talking to Michele at the conference in Poland and saying, okay, what you would have to do is just make sure that nobody can beef the beefer. And this could be an actual real problem, because the attacker cannot trust the attack website anymore. This sounds a little bit icky when the attacker cannot trust the attack website anymore, but the website could always start sending back bad data and use Beef against the beefer. And with the sealing technique, when you just go along and seal this object, this Beef object, this global variable, and make sure that the defender cannot modify it anymore, you have a tamper-proof Beef, at least on modern browsers, and you can make sure the defender doesn't fire back at you. So it's not maybe the most usual use case here, but it's an interesting use case to consider in case you plan something bad with object-defined property, which is possible as well. So you can see you can do good things with it, you can do bad things with it. So you have to kind of, as a web developer, you have to kind of obey to a new rule. And this is the order of deployment is everything. You have to be the first one to deploy a benign JavaScript or the JavaScript you created or you trust. If you do not deploy as the first one, anything can happen. Like anything is possible then. Because the attacker can as well deploy some stuff which is sealing objects, which is sealing your global functions, giving them some complete different meaning, some complete different purpose. And you don't want that as a developer. And basically, we are boiling it down to being able to say the script deploying first controls the whole DOM. Like after that, nothing more is possible which is not authorized by that script, if that script is hardcore. Now we have a little fun snippet, because if you, for example, are a bit afraid of object-defined property right now as a JavaScript developer, I can just say self-defense is possible. You can completely switch off object-defined property. How would you do it? Who knows how you can completely switch off object-defined property? Well, it's easy. Just define property, and then you're gone. Just make sure you take object-defined property, pass an object, define property, say it's empty, it's configurable false, and then that was it with the object-defined property. So now it's gone. Like it will never return unless you reload the page. If the attacker then goes along and tries to define something, tries to, for example, redefine the setter or getter for window variable secret or the member secret, and says like, hey, I want to define it to be accessed with the method steal info, then there will be a type error. So object-defined property is dead now. Let's reflect on what we've seen so far. Where are we now with ES5, and can we actually use it to end XSS? Kinda. In some situations we can't, in most situations we can, so we're already there, almost there. The pros we have, we can fully restrict property and method access in the DOM, which is nice. It's be done tamper safe. We have the actual foundation to build a client-side IDS. There is none out there, so if you want to build one, you would be the first. Like, build it, it's necessary. And we have the foundation for a client-side role-based access control system. We can fully regulate object access, object extension, object modification, everything which is happening with every single DOM object. We have perfect support from, for example, CSP and sandbox iframes, because if you combine these three things, this technique plus CSP plus sandbox iframes, you have a very, very thorough and very, very comprehensive protection framework in your DOM, combined with the features your browser is giving you. There are sub-contrasts, of course, as well. It's a blacklist. So far, it is a blacklist. You cannot just go along and say object define property window and set it everything to false. This is not working. We have these magic properties which are causing problems. One of them is location. Like if you assign a string to a location which is nesting a string, then you bypass the system. That's just a big hole in there. We have to urge browser vendors to give us better ways of dealing with location and JavaScript URIs. Browser vendors were already fixing over the last years all these problems with data URIs. Now they have to fix JavaScript URIs. If that would be working, and if a string assigned to location would not generate a fresh DOM without the protection, then we would be fine. Then this would have been the last gap to close to make the system really work. Right now, the DOM completely sucks. And I'm going to show you some more reason why it really sucks. Still, we can build a client-side IDS, we can build a role-based access control system, and we can pick important properties, we can pick the goodies in our throne room to protect and to make them not be accessible by the attacker anymore. The adaptation might not be the easiest one, but the thing is, the best way we figured out would be to actually contact the library authors, such as jQuery, provide an implementation for jQuery and jQuery-based IDS, which is possible. We have the prototype running. I can show it to you later on. We are aiming towards creating a UA-based tool, which is allowing you to define possible policy files, saying like, okay, this should be touchable, this should be accessible by this method, and so on. So you have it clickable, and you don't have to write JSON or something like that. It's most likely to spit out JSON afterwards for the actual policy and configuration file. And we hope to be able to put up a prototype of the current version soon to to make it available for public testing and see if people can break it. But I think that anything which is not community tested is breakable. So a solution like this should definitely experience community hardening and community testing. And we are also trying to find a way to interface server-side filter logic and find a way, but this is in the future, to be able to tell the server about the major and the key capabilities of the client. What is happening here? Is there still a backtick trick? Can we make feature tests against bugs and so on? So there is a lot of work to do. And the most important part is, of course, spreading awareness for security's sake. Tell people about object-defined property and tell them what is possible with JavaScript and modern browsers right now. Also, we need to fix the DOM. Like, the DOM is completely broken. Any one of you heard about the add event listener black hole? Like what this is? So if you have a property or if you have a markup element, like let's say the body element, and you assign an event to this one with add event listener, and then you have a look at the DOM, you will find no representation of this event assignment, like nothing. The DOM is still the same. It's all happening in C. It's all happening in the browser code. It's a complete black hole. If you then go ahead and assign an anonymous function for this event, you cannot even remove it. It's there, the event fires, but you cannot see it. There is no representation in the DOM. Try it out. Find a difference between DOM A, then assign the event, and then have a look at DOM A again. Compare them and see if there is a difference. There is none. It's just completely invisible. We have to specify a whitelist-based approach, which is giving us the possibility to say seal everything, but this is not possible right now, but would really help the adaptation, really help the implementation. And we have to fix some of the DOM events, especially one of the DOM level 3 events. We have right now DOM sub-pre-modified, which is telling us after a modification has taken place what the modification was. But this is useless knowledge. We don't want to use it. We want to use it before. So what we need to specify is a DOM before sub-pre-modified. So giving us the possibility to find out what a certain function is doing before actually modifying the DOM, how it's going to be modified, then being able to control it, to monitor what's happening here, to decide if it's the right thing or not, and then have the modification happen.
Not possible right now. Right now we have a race condition, but with such an event, which is future work, we would be able to do this and solve the continuity problem here. We definitely need DOM proxies. There have been some publications about DOM proxies, but there is no implementation yet. And basically, as a router, we can say the DOM needs more trustability. Right now, we cannot trust the DOM at all. Like the live demo showed that anything can happen in the DOM. In any browser, there are artifacts like the ones I showed. And of course, one of the major part of future work is to monitor ES6 and ES7 and see what's going on there, what harmony proxies are going to bring and stuff like that. Future work 2, and this is one of the last slides. We need to address browser vendors about concerns and bugs. This already happened in the past. We were contacting the Firefox team. We were contacting even Apple for a bug and Safari with double freezing. You can just freeze the property and just freeze it again, and then it had a different state. Like, this should never be possible. We need to find better ways to treat JavaScript URIs because they are really causing problems in many, many applications and many situations and in many attack models. And we have to find a way to actually provide a safe and homogeneous DOM. So if you have a look at the DOM of browser A and have a look at DOM of browser B, you don't find too many differences anymore. Right now it's catastrophic. Like even a simple event is yielding completely different objects depending on what browser you use. It's definitely time to create a model framework to show our approach. We have a prototype running for malware detection. Whoever wants to see it afterwards over a few beers or something, just come at me and ask me to show it. It's running, it's working. We have to learn from other sandbox approaches. I don't necessarily believe in JavaScript sandboxes because we broke about everyone which is existing out there, except from Google Kaha, which is running on the server and really a monstrosity of a sandbox. But Dojo sandbox took 5 minutes to break, so it's not a sandbox. It's just a playground, nothing more. So basically we have to learn from other sandbox creators' mistakes and use it for a proxification approach. There are more academic publications to come, and we hope to be able to spread more awareness on ECMAScript 5 and the attached implications. And finally, and this is one of the most important things here, we somehow have to tell online advertisers what other online advertisers they are sharing advertising slots with are faced with. Like this whole object overwriting and object freezing thing is a catastrophe for online advertisers because they can cheat on each other like hell. Like there's no way they can control anymore that the properties they are working with are really the properties they think they are working with. And for them, it's really a financial catastrophe if they are being attacked with object-defined property and modified objects that cannot be reset anymore. So, last wrap up. XSL is still undefeated, but we're working on it, and I think we're a little bit closer to actually defeating it by doing it in the DOM and not doing it on the other layers anymore. Like, we cannot fix it on layer 3, 4, 5, and 6. We have to do it in the browser. There's no different way, in my opinion. Rich internet applications are gaining complexity and power. There's more and more internet applications going direction e-government, verified users. In Germany, we have like this mailing system where you are you. If there is an XSS in there, it's catastrophic because everybody can forge your identity, your trusted, proved identity. We've seen that client-agnostic server-side filters, such as HTML Purifier, are working quite fine, but in an actual, real, sophisticated attack, they're just designed to fail because they have no insight on what's happening on the client. They don't know the capability. And we've learned that it's definitely time for a new approach to tackle XSS. We've seen that there's still a lot of work to be done, and, well, no one said it's going to be easy, but I think this might be one way to actually solve the problem. And, yeah, that was it. That's the last slide. Credits where credits are due. Thanks a lot to Gareth Hayes for his work, Stefano Di Paola, Eduardo Vela, Jon Willander, Matthias Berkling from Sweden, Jonas Magazinus from Sweden, who was publishing about lightweight self-protecting JavaScript and has deep knowledge about attacking it. Michele Oro for Beef, Fung et al. For their approaches of trying to fight proxification-based solutions of self-protecting JavaScript and all the unmentioned contributors. And I hope I'm not too much over time, so if there are any questions, shoot me. Thank you a lot. Anyone? We're 7 minutes. There we go. Okay.
Do you have any idea what would be the impact in terms of performance of implementing client-based IDS inside the browser?
Yes, we actually measured that with a prototype, and the performance data is not super good, but not super bad. On a dual-core workstation, we have a median of 8 milliseconds. of delay, which is almost not noticeable. On a EPC 1000H of ASUS, we have a delay of, I think it was between 30 and 40 milliseconds, and on a smartphone we had a delay of, I think it was 60 to 90 milliseconds. But there is a publication on the way where we have like performance tables, and you can look it up, and if you want to copy, let me know. So it's not really noticeable by the user, but if the application really stresses against it and really wants to find out if there is something like that with a timing attack, then it's possible. So it's not completely invisible. There is a minor footprint, timing-wise.
Shouldn't that pose the number of functions that would be whitelisted or blacklisted?
What do you mean?
Shouldn't be variable with the number of functions of elements of the DOM that you're currently working with or sealing or checking the roles?
Let me quickly describe what we did with the prototype. We were iterating over the existing DOM properties and sealing them with a centralized method. The actual number of sealed methods per DOM was about 30 to 50, depending on the DOM on the website. And we tested it on Google Maps, on Twitter, on Google Mail, like a local copy of the Google Mail DOM, and so on. So these were applications we tested upon with a lot of stuff going on in the DOM, a lot of interactivity. And we took the times from these applications. So the median was 8, 30-something, and 60-something. But of course, like if you want to force it, you can still detect and slow down such a system. So one example would be to actually severely slow it down is doing massive string concatenation with concatenation methods and not using, for example, the concatenation operator plus or something like that. Then you can easily slow it down. If you have like 30,000 concatenation steps, this will just take time and you will just wait as a user. So this would be a valid timing attack or a valid way to just DOS a website using a system like that. But if you have a loop iterating 3,000, 40,000, 100,000 times, you can DOS anything. Just did that answer the question?
Yeah.
Okay, thanks. Anyone else? Okay, so that's it. Thanks a lot.